Hello everyone, my name is Kung Nguyen and I'm a third year aerospace engineering student. And in this video, I will talk about our first lab, which is called digital sampling. And for my experiment, I will do a comparison of guitar notes. So the objective of this experiment is to familiarize ourselves with digital data acquisition of time-varying signals, and it also serves as an introduction to digital data acquisition system. And the motivation for this lab is that most experimental measurements involve the dimension of time, and we are interested in measuring variables that can be described by waveform. Understanding these waves will allow for more accurate data collection in the future. For a bit of background knowledge, we have to know about the sampling theory and aliasing. So what we measure is the continuous function Vt, which is sampled at unevenly spaced intervals in time. The sampling frequency or the data acquisition rate is Fx equal to 1 over delta t. There's also the Nyquist frequency, which is half the sampling frequency. This is also the Nyquist-Shannon sampling theorem that states if the waveform contains no components above the Nyquist frequency, then the waveform can be completely determined by the sample data. There is also something called aliasing, which means that information at the higher frequency can show up at the lower frequency. So for the first week of the take-home lab, which is week 2, we had to perform some initial waveform identification. So we have 11 audio tracks that we had to identify in the waveform. So for the first track, it is a sine wave at 100 Hz. The second one is the sine wave at 1000 Hz. The third is a triangle wave. The fourth is a square wave. The fifth is also a sine wave, but this time at 3000 Hz. The sixth is a round wave. The seventh audio track and 8 is also like they were both noisy sine at 1000 Hz. The ninth audio track is a sum of 3 sine waves at 100, 1000 and 10,000 Hz. The 10th audio track is a product of 2 sine waves at 900 and 1100 Hz. And the 11th is the sine of sine wave with a varying frequency at 50 to 1000 Hz. For the week 3 of the lab, we had to validate our microphone input response, and we had to measure how well the microphone responds at 9 different frequencies. For my experiment, I chose the frequency at 20, 50, 500, 1000, 3000, 5000, 6000, 8000 and 10,000 Hz. And the procedure is really simple. I have to measure 9 frequencies using the audio jack, and then I measure 9 frequencies using the microphone. After that, I calculate the relative response by taking the file from the microphone at each tone frequency divided by the file from the audio jack at the same frequency. So here's what I got from the validation. As you can see, all the relative response is less than 1, which means the audio jack outperforms the microphone at data acquisition. So now is my approach to my experiment. So the equipment I got is the DAQ system. I also have a microphone and an audio jack that came with the system. I will have my own guitar, which is an acoustic guitar, and there's also a virtual tone generator. And for the procedure, I just play 9 notes on the same string using the virtual guitar online, and I will record that using the audio jack. After that, I'm gonna play 9 notes on the same string using my guitar, and I will record it using the microphone. After that, we calculate the relative response. And here's the result I got from the experiment. So I concluded that as you go into higher notes in the guitar string, the frequency increase, as you can see here. There's also the same thing we encountered back when we validated the microphone, is that the audio jack outperformed the microphone in the data acquisition because the relative response is all less than 1. There was also a lot of white noise when I was using the microphone, which means I have to use the dampers for future experiment. Also, the relative response graph varies significantly across different frequencies, so we can utilize a low-pass filters for future experiment. Thank you.